very much for your help. And now I can see that you started recording. So welcome to the first class in category theory. And the first lecture is going to be about categories, functors, and natural transformation. So category theory was born in 1945 by the genius of Eilenberg and MacLean, and they were working in algebraic topology. And for them, category theory was a tool in order to organize some standard constructions in algebraic topology. So from the historical point of view, category theory was born to organize knowledge in mathematics, even though later it became a topic per se, and of course nowadays is a research topic as many others, but still it's used in many fields of mathematics like algebraic topology, algebraic geometry, and even in logic, even though classical logicians are very often against this language. So category theory should really be understood as a language in which that we can use in order to talk about the mathematics that we like the most. For example, myself, I'm mostly a logician and I speak the language of category theory in order to discuss about logic. So let's go directly to the definition. What is a category? So unfortunately, I have no feedback from you. So I don't understand if you can hear me. I cannot see your eyes. So it's a bit hard for me to understand whether you're following. So maybe I encourage you to ask questions and make comments in order to be sure that you are still there and you're not dead. Okay, thank you. So definition of category. A category A is, or let's say, consists of the following data. So first, we have a collection of objects that some people call ob-A, even though, let's be honest about this, we will always call it A. So we will use an abuse of notation all the time, and we will just call it A. Then we have for all A and B in A, so already you see this abuse of notation, we have a set that we indicate like this, A between A and B. Some people use A from A to B. I will always use this notation because it's less, it's more compact, I would say, though this one is a bit older and some people might prefer it, I'm not sure. And then what we have is for all A, B, and C, a function that we indicate with this little circle, which goes from A, B times B, C into A, C. Okay, let me highlight a couple of stuff. So we have a collection of objects, then we have this sets, and then we have this function. So let's try to discuss it a little bit. What's the idea behind this function? This is called composition. And we will, of course, I will comment it in a moment, making some examples. So for the moment, I will try to finish with the brute, the crude definition. So this composition should obey to some associativity. So this is associative. which means that if I have H composite with G and then composite with F, so this is called, I'm not sure if this is the Polish notation, or the Polish notation would be this one. So one is called Polish notation and the other is called, I think, infix notation. But anyway, of course, we use this notation, and I guess everyone in the audience is experienced enough not to be scared by the notation above. Okay, so this one should be the same of H composite with G and then F. Okay, and of course I read from right to left. So the first one is this one, and then the others going to the left. And then the last axiom is that for all A in A, there is an element one of A which belongs to the Ohm set of AA. Okay, again, here there is an identity law which just says, I will write just one axiom, otherwise I become extremely boring, which just says that 1A composite with H is the same of H, and of let's write also the other one, H composite with 1A is H. Okay, so up to this point I didn't say much. This is called identity law. And this is called associativity, as I mentioned. So forget for a moment about these two additional assumptions, which are some properties. What really matters is that we have this collection of objects, we have these Ohm sets, and then we have this composition. So let's make maybe a couple of relevant examples. So the first example is set. So this is the name of this category. So before it was called A, and the objects of set are sets. And then for every A, B sets, set AB is the set of functions from A into B. Okay, so this is a very standard example, and this is a good moment to say that in this definition I was not precise, and I didn't want to be precise. Here I only said that this is a collection of objects, meaning that it might be a proper class, like in the case of sets, of course. This is a proper class. While this one instead is always a set and will never be a proper class. These are called locally small categories. And this word locally refers to the Ohm sets. And so small means that it is a set, okay? So for example, could you guess, so someone should say something here, could you guess what means locally finite category? This should be an easy question.
But I would say that all ohms between set A and B should be finite sets, no?
Yes, precisely. Yeah, that's very correct. So AB is finite for all A and B. And of course, the most natural example for this is the category fin set. This is the category whose objects are finite sets. And for every couple AB finite sets, then fin set AB is functions from A to B. Okay, so this is a complete triviality. Of course, there is nothing deep here, but this is a good example of a category which is locally finite. And instead, this is a category, set is a category which is locally small, though it's large. And when people say that a category is large, they mean that the objects are essentially a proper class. So I will comment on this word essentially later in this lecture. For the moment, I would like to give you a very broad collection of examples. So another example is the category of topological spaces. So what is this category? So I'm sure you are familiar with it. I will try to use a more compact notation. So here we have objects are topological spaces. And arrows, so top, A, B, are continuous functions. Okay, so this is a good moment to comment on the composition that I defined before. So what is this composition in this case from top AB times top BC into top AC? So this is just, you take a function f, you take a function g, and you send it to the composition as set functions. So first you do f, and then you do g. Okay, of course, again, this is reverse notation. I think everyone is used to with it. And you see, it's evident that this composition obeys to the axioms I put before. So that's why I didn't comment too much on this this example. So of course, then we have also the identity, and the identity is just the identity function, which goes from a topological space X into the topological space X, which is of course a continuous function. And in the previous example, composition of continuous function is continuous, and so this really makes sense, this notation here. Okay, good. So let's make another couple of examples. Another example is group. So objects are groups, and morphism are a group homomorphism. And of course, here I'm sure you got the pattern. So for example, let R be a ring. Then we can define R modules. And here we have modules and linear maps. Yes. Of course, one great example of this is K-vect, which are just R modules over a field. Then let me close with two examples which I really like. Let me close this first load of examples. So we have also rings. So this is the category whose objects are rings. And then we have ring homomorphism. And observe that it doesn't matter what I mean by ring. They might be commutative, they might have the unit, the homomorphism might preserve or not the unit. It doesn't matter. They always form a category, and it's quite evident, at least in my opinion. Please, if it's not, you can interrupt me, that this is a structure of category. So all these examples are examples all the examples above are mathematical structures. So we have a family of mathematical structures, say groups, for example, and we organize them in a category. So there is maybe Z, then there is Q, which is also a group, then there is real numbers, and then we have all these functions between them. So a category is a kind of graph, after all, where we can compose edges. So let's put here, I don't know, this is the trivial one, where we can compose edges in one direction and the other, and this composition of edges are additional structure properties of this, or structure, it doesn't matter, of this graph. Okay. So this is how category theory was born. People had to study constructions between categories, between mathematical structures, let's say, and they used the concept of category to put all the structures of the same kind in the same group. So for example, groups is a category, and then we saw many others. We saw rings, groups, topological spaces, and set, for example. For another example is given a theory T. We could say first order theory, we could say infinitary, doesn't matter. We can look at the category of models of this theory. And here we could choose elementary embedding. Or we could just choose homomorphism, yes. And in both cases, this would be a category, because composition of elementary factors is still elementary, and composition of homomorphism is still an homomorphism. And of course, the identity is an elementary embedding. Good. So these are natural examples of category. And before proceeding, may I ask if everything is clear up to this point?
Yeah, Ivan, sorry, just one thing. In the definition that you gave at the very beginning,
yes,
you put that you have a set home AB, no?
For each AB. So for each AB, I have this set, yes.
And locally small, doesn't it mean that this is a set, no?
It means that this is a set, of course.
So, but I mean, doesn't your definition imply that category you include being locally small in the definition?
So in the definition I gave, yes. Though, of course, you could just be a little bit more flexible. And so my definition of category is locally small category.
Okay,
but of course,
okay.
You could decide to be a little bit more flexible and here to allow for classes of homomorphism, or even more restrictive and require this collection to be a set. This collection here, you could require to be a set. So in this course, we will mainly study possibly large but locally small categories. And sometimes we will study small categories in the sense that OB is a set, but I will always say it when we do, because this is a very strong restriction, as it's evident, yes? Okay. So for example, in the examples I gave you, this is set is large but locally small. Finite set, so it's technically large, it is locally small, but it is also essentially small in a sense that I will point out later. Just give me a couple of minutes. Then topological space is possibly large. It's definitely large, but locally small. And also the others, groups, rings, these are large but locally small. And also T modes for a theory. And by mode, I mean models of the theory, of course. It's not important that you manage to understand all the examples, because maybe you come from Banach spaces, maybe you come from logic, it doesn't matter. What matters is that you understand some examples at least. So again, categories were born in this way, but this is not the only way we can use categories. So one thing that is very wrong is to think that a category is always a category of structured sets and decorated functions. So of course, all the examples I gave you are of this form. So for example, top, then there was groups, then there was rings, and of course, also set is an example of this. So many categories fall under this definition, but it is not true that every category is of this form. Let's make an example of a category which is not of this form. So these examples, please be careful because they are quite important. So the first example that I would like to point out is let P be a poset. So poset is a partially ordered set, yes, with this less than relation on it. And every poset is can be seen as a category. So let's define, maybe I will change a little bit the notation. I will call it in this way. So the objects of this P are so objects of my new category are the elements of the poset, yes? And then I say that P between A and B is either it is empty if let's put it, sorry, let's say either it is let me change, it is top if A is less than B, and it is bottom otherwise. Okay, so this is a definition. Technically both of them are sets. And now what's the point? So the point is that and I should define you a composition law here. And so the composition is more or less trivial. So let's say PAB times PBC into PAC. Okay, and so what's the idea here? It's very easy. I just define it by cases. So if I have top, I send it to top. If I have top bottom, I send it to bottom. If I have bottom, I send it to bottom. Okay, did I finish all the possibilities? Sorry, there is also bottom top, which I send to bottom. Okay, so if you think about it, so this might look as a complicated example, and indeed it wants to be more complicated than the others, but after all, what I'm doing is I'm just encoding the structure of poset inside the structure of category. So because this, so what this is saying is that PAB, so this, I mean, top is like the relevant element and bottom is false. So PAB is positive if A is less than B, otherwise it's negative. So what I'm doing, I'm just trying to write down the poset structure. And so after all, I'm just, what's happening here is just I'm rewriting the structure of poset in another way, even though this data is precisely equivalent to that of being a poset. I'm just rewriting in another way. And this example will be very relevant very soon. So for example, let X be a topological spaces. Then we can define O of X, and this guy is a category. And who is this category? It's the category of opens and then I say that there is a function from A to B if and only if A is inside B. Yes, So after all, this is just the same of I'm describing the poset of opens as in this example. Okay, so this is just a special case of the previous construction. Of course, I'm already cheating because I changed the specification because here I'm doing it with the empty set and the set with one element, but this is evidently the same of choosing top and bottom. I'm sure everybody agrees with it. Okay, so another example which is very important and which falls into this kind of pattern is, so take let C be a category with one object. Aha, but this looks like a very strange guy to us, doesn't it? So we have this object here, little c. This is the only guy in our category. And then by definition, we have C. Yes. Let's try to understand with this CC. So of course we have a definition. We have a notion of composition. And then we have an identity. But we know this mathematical structure. What is it? So this one is a monoid. So this means that every monoid can be seen as a one object category. So in general, this is called M, or maybe we could change the notation a little bit. So given this monoid M here, I define a category M whose objects, there is only one object, and it's this, and then let me call it C, okay? And then M between C and C is precisely our monoid M. So it's the set M together with the composition and the unit of M. And this allows us to see monoids as categories. And of course, also groups as categories, because these are just very special monoids. So these two examples are not so easy to grasp. So I would like to ask everyone if you had understood these two examples. So please say no if you haven't. Okay, so I guess everybody has, and this is very important. So if you haven't, please stop me, because these are the two examples to which you might not be used. So I would like to close with other two examples. So there is a special category which is called cut, and the objects are small categories. So when I say small category, I mean that the objects are a set, okay? So this is the category of small categories and functors. And this here, it's very important. I haven't defined what's a functor, so I will finish this example in a moment. But I mean, why did I say it now? Because it just shows that a category per se, it's nothing we care about. What matters is the way categories behave with each other. So what is a morphism of categories? And this concept will be the concept of functors that I will introduce in a moment. Another example, which is very important, is the category pos, whose objects are posets and morphisms are monotone functions. And this example obeys to the previous family of examples, the easy one, so I will not comment it anymore. Notice that a poset itself can be seen as a category, while the class of all poset is a category per se. So category theory can be used to describe very small things like a poset, or very large things like the category of poset itself. The same with cat, which we will describe a little bit better later. So one important construction with categories is that of dual category. What is a dual category? So given a category C, we can produce another category that we call C-op. And so this category is called the opposite of C, or sometimes called the dual of C. It doesn't matter which notation you like. So the objects of C-op are precisely the objects of C, while the morphisms, so C-op from A to B, is precisely C from B to A. So you see, I'm saying that a function from A to B is, by definition, a map from B to A. So dual categories are something very hard to understand, but I'm sure that some of you have an example in mind. Do you have an idea of a concrete example of a dual category? So when I will write it, it will be evident, I believe. So given a poset P, we see it as a category, and then who is P-op? Well, poset associated to a category, sorry, let me rewrite. Category associated to a poset. So who is P-op? Well, this is precisely the category associated to the poset P-op, which is the opposite poset, where we say that A is less than B if and only if B was less than A in the previous poset. So let's write this notation a little bit better. Okay. So again, this example, in my opinion, is not completely easy to understand. And to be very honest with you, I didn't understand the notion of dual category the first time I saw it. For example, it's very hard to understand, and we will see it in the course, with the opposite category of sets. Definitely, it's not the same of the category of sets, even though I didn't tell you what I mean by same. But the example of opposite poset is an example that I believe is understandable to you. That's at least what I hope. And of course, during the course, we will see many examples of this construction. So it's going to be easier for you to get acquainted with this example. There is one very nice exercise in the exercise sheet I gave you about this concept. So finally, now that we have some examples of category, we can come to the star, to the main character of this play, which is the concept of functor. So a functor is a way to compare categories. And in a sense, functors are two categories, like I would say functions are two sets. So they are a way to compare or to transform categories one into each other. So let's give the definition and then we will see some examples. Of course, the aim of this lecture is to give you as many examples as possible. So many examples will be very well known to you, but some others maybe might open new ideas. I hope so, at least. So what is a functor? So given two category, A and B, a functor is, so a class function going from the objects of A into the objects of B. Maybe I will call it F, okay? Then we have, for each A and A prime in A, we have a function which goes from A, between A and A prime, to V between F of A and F of A prime. So it's also an assignment on functions. It gets transformed in something like this. And of course, we want this assignment to behave nicely, which means that f of f prime composite f should be the same of f of f prime composite f of f, and f of 1 of A is 1 of f of A. So it's a kind of homomorphism of algebraic structures. So these two equations, let's try to understand what they mean. So for example, in this one, we have f, g, but then we also have this composition. And we want that so here we have f of f, here we have f of g, and here we have f of gf. So of course, these are equal by definition because this was a category. So we want that also this one are equal. This is what means that f is a functor. And of course, a similar requirement is what is meant by this one. So I will not write it. So it just means that it is a homomorphism with respect to the structure of category. So now examples. So maybe one example is the identity functor. Let's say from set to set. Of course, it doesn't matter that it is set. I could have chosen another category. It really doesn't matter. And this is the functor which sends every set A into itself and every function into itself. I mean, this is a very stupid functor in a way. Then another example is a cluster of examples which are called forgetful. So what is this class of forgetful functors? For example, let's take topological spaces and let's take sets. So forgetful functors are all very often indicated with the letter U, which stands for underlying. And it sends a topological space X. So maybe to be more precise, a topological space X tau, where X is the set and tau is the topology. I send it to the underlying set X, and a continuous function, I send it to itself. So it's the functor that just forgets that we were talking about topological spaces and just takes the underlying set. So this is, as I said, a family of examples. We can do it also with groups. And we can do it with modules. What we are doing is always the same. We are forgetting the structure. So we map a group to its underlying set. We map the module to its underlying module. Yes, maybe I will write some others of them. We have also ring into set, but we also have, for example, another one is abelian groups into groups. So this is just the functor that takes an abelian group and says, look, this is just a group. So it sends the abelian group A into itself, essentially. Though functors are not always dumb. So let's make an example of a functor which is complicated in a way. So the first complicated example is the abelianization functor. So this functor goes from group to abelian groups. It takes a group and it quotients by its commutator. So some of you might not know what is the commutator. In that case, I will make other examples of interesting functors. So just wait a second. I also have to tell you where I sent a group homomorphism, F. And so the idea here is that I send it I just observed that every group homomorphism must send the commutators into the commutators, and so it can be mapped to the quotient. So let's make it more precise. We have our F. Here we have the quotient. Here we have the quotient by the commutators. And then you can observe that F must send commutators to commutators. And so there exists a functor F, a morphism F bar here. And I map F to F bar. And this guy is unique. So this assignment really makes sense. And this quotient is always abelian. So this construction is what people say functorial. And it's extremely easy to check that it preserves composition and also it preserves the identity. So I will never check this because you are grown-ups. You are not babies. I will not check it. Sorry, no COVID. Then another example that everybody probably knows is the pi one. So the pi one goes from topological spaces star into groups. So topological spaces star is the category of pointed spaces which means that you have a set X together, sorry, a space X together with X0, which is a point in X. And then a function between them is a continuous function such that f of x0 is y0, okay? Good, so this is my notion of top star, which is my category of pointed spaces. And then what's the functor pi1? It sends a space x, x0 to the pi1 of x with base x0. So this construction is extremely well known to topologists. So, and to people that are not topologists, I mean, it's a bit long to define the pi1, so I will not comment it. And then it sends f to the class of f. So this construction is well known to the people that should know. And again, it doesn't matter that everybody understand every example. I just would like to show that there is a very broad family of examples. Of course, the case of of forgetful functors, it was here. Another case of forgetful functors goes from T mod, so models of a theory, to set, and you just forget the structure of model. I mean, to be precise, this is an example of, and also this one, and also this one, and also this one. So all of them are examples of this behavior, in which you just forget the structure of model that you have on the set. Okay. So now, so let's talk about free functors. So free functors are a very broad family of examples, which are extremely interesting, and they are like very important in algebra and universal algebra. So the first example is from set to vect. Okay, I will call it f. Sorry, could you confirm that you can hear me?
I can.
Oh, very good. Sorry, I'm getting a bit. Okay, so it sends a set X to the free vector space over X. So let's say vect K. I mean vector spaces over K, which is my favorite field, the one you choose. So this is K of X, and this is by definition something on the, words of the form sum of Ki with Ki in K. Xi. Yes, these are formal words. And then I send a function f to the function, let me call f of f, which goes from this to this. And it sends this word to some Ki f of xi. And of course, this does make sense because this guy is inside y and thus is in the basis of k of y. So this is really a functorial assignment. And in the class of free functors, we have many examples like this. So for example, we could go from set to abelian groups, sending x to zx, which is precisely, I mean, it's the same example after all. We have sum of ni xi, and then everything is the same. And then we have other free constructions, for example, from set to group, which sends little x, x, then to the free group over x. So the free group, it's well known. This is something like xi, x2, x3. So just a position of letters. It must be finite though. And of course, in the case of the function, it works in the same way of the previous examples. So I will not be too boring with this. But free functors are a very natural class of them, of functors, which don't behave trivially on sets. So they are not like the forgetful functor. And they are used in algebra, and they are called free constructions. So everybody is quite used to them, I guess. Another example is from set to top, which equips a set to the set together with the discrete topology. And of course, then you just take the same function and you check that it is continuous with respect to the discrete topology. Or similarly, you can map x to x together with the indiscrete topology, which, I mean, it's really the same example, and it's very easy to check that f is continuous with respect to this choice. So in this case, we really have three interesting functors to look at. We have the forgetful functor, and then we have the discrete topology, and then we have the indiscrete topology. Okay, so, and in a sense, disc can be seen as a free functor, but we will see this in the next lectures. Very good. So another example that I really care about is the functor which goes from posets to cuts, to cut. So again, cut is in cut we have categories and functors. And I didn't tell you, but this is quite evident, functors can be composed. So if I have a functor f and a functor g, then f composite with g is still a functor. And again, there is not much to prove there. So what is this functor? Can you think about it? You have a poset and you would like to associate to it a category. Does someone have an idea? Well, we saw this together. It's just the category poset P, which we defined before. This example here. So to every poset P, we can associate this category, which I called in this way, matBB_P. And to every function, we really get a functor in this way. So let's discuss it a little bit. So we sent P to P, and again, this as the objects are elements of P, and so P A B is 1 if A is less than B, otherwise is 0. Okay, so this is the assignment on objects, and the function is just sent to the function. So the monotone function is just sent to itself, and we can check that this is functorial with respect to the structure. In fact, what you can check, even though I will not do, you can do it for exercise, is that every functor between these two categories is precisely induced by a monotone function. So I will call this functor I. Okay. And in fact, we can also go in the other direction. And this functor here, I will call it maybe like this. It's a quotient. And it's a functor that takes C and associate to it a poset. Which poset? So I will call it C modulo tilde. And what's this poset? What's this poset? So the elements of the posets are the objects of the category. And then we say that A is less than B if and only if there is a function, if and only is, sorry, let's say in this way, CAB is not empty. Okay? So of course, to be precise, this does not make sense. We have to take the smallest equivalence relation generated by this, but this can clearly be done. And so we get a poset out of it. And this poset is just a poset which says, okay, look, you have your, say, groups, for example. This is the poset which essentially collapses all this to only one point. So in this case, like this component would be just 1 point, which is C, the same of R, the same of Q, the same of C. So this is not a very interesting poset because in this case, this category is very rich of morphisms. And so this construction is extremely stupid. Though, if you apply this construction, if you take this composition, so you take this quotienting construction here, and here you just take I, what you get here is more or less, and I will say what means to be more or less, this is more or less the identity of pos. This is quite intuitive because in the case of this precise structure, so the categories of the form I of P, they are not very rich of morphism, and so we are not quotienting by much, and so it's quite clear that this construction just gives us back the poset we started from. Okay, so I will stop for a moment and I will ask you comments, remarks. Did you understand up to this point? Would you like me to go slower? I'm listening. So I have to say you are forced to say something. You can't say everything is fine, but you must say something. Did I miss all of you again?
I think everything's fine.
Okay. So there is someone that is trying to say
construction in this example. Sorry,
so
can you hear me?
Adam, we can hear you very badly. Could you repeat?
I just wanted to ask, with this previous example, when you did this quotient of category
Yes.
here, so because I got the impression that from the definition you are not collapsing the objects, right?
Yes, but as I told, yes, you're right. But as I said, you get collapsed the objects here because so in this way, this is not completely well defined because when you say here that A is, you say here A is less than B if and only if there is a map. So for example, look at Z and Q. They are the same then because A is less than B and then B and then B is less than A. So A is the same of B.
Yeah. how is it called? Quasi-ordered set. But if you want it to be set, then
Adam, I'm extremely sorry, but we hear you very badly, and I hope that you don't hear me this badly, because I understand nothing of what you say, and I hope
I'm sorry, I think this connection here on Eduroam is currently very bad, but I can hear you.
Oh, very good. Then I'm sorry. Can we discuss this in person maybe later? And for the moment, I will proceed. I'm sorry. I hope everybody can hear me well. And thank you, Adam, for this question. I hope at least I gave you the correct idea. Then we can discuss it in person. Now, so for the last part of this lecture, there are still two things I would like to tell you about. So the last things are contravariant functors, then I would like to tell you about faithful functors, and then I would like to tell you about natural transformation. So these are the last three topics of this lecture. I wouldn't like to speak for too much time because the attention span of researchers is shorter and shorter with their age, especially mine. And so let's go with what is a contravariant functor. So let's make a very well-known example. So for example, take X a space, okay, maybe a manifold, because we want to work in a very regular world. And then we have defined together the category O of X, and this is the category of opens. So again, this is the poset, the category associated to the poset of open sets, yes? Now, we can define an assignment that takes U and send it to what? What happened? To continuous functions from U into real numbers, okay? But now, if you think about it, given a function like an inclusion from U into V, which is another one, when we look at continuous functions from V to R, we don't have a natural map defined in this way. Instead, we have a natural map defined in this way, which is the restriction. Okay, I think this should be clear to everyone, because when you have a function from V into R, you take the composition and then you get a map I star in this direction, which just maps F to I composite with F. Yes. So here what's happening is that this construction is not functorial, because given F of U and F of V, we don't get a map in the same direction. Yes, I think this should, I mean, from the definition I gave you, this is not functorial. To be precise, it is not a functor from O of X into a set. So again, it is not a functor because the assignment goes in the other direction with respect to arrows. Do you see a way to fix this problem? Yes, so there is a way to fix this problem, is just to take it from the opposite category, because in this way, this I goes in the other direction. And so it is functorial. So to be precise, opposite categories were invented to deal with contravariant assignments. Like in this case. So for us, in this moment, they are just a technical tool in order to make stuff which are not functorial, functorial. Though we have to change category of domain, like in this case, because this category is the opposite poset and it's not anymore the poset we started from. And this is very important because imagine you start from a poset which has a bottom but has no top. Then the opposite poset has a top but has no bottom. And so the two posets are very different. Don't forget it. They look similar, but they might be extremely different. They might not be isomorphic, for example, as posets. Okay, very good. For example, if a poset has a bottom but no top, and the opposite has top but no bottom, then evidently they cannot be isomorphic. This is clear because isomorphic posets have either have bottom or don't. So, okay, so contravariant functors are a new example of functor, and this one is called in the literature sheaf of continuous functions, and it's a very important one. So this is relevant in sheaf theory and algebraic geometry, for example. In fact, this is the basis of the theory. Now I would like to define, so what did I do? Yes, I defined contravariant functors. Now I would like to define faithful, conservative, and full functors. So definition, a functor is faithful when for all A and B, when we look, a functor f which goes from A to B. For all A, B, when I look at the function which goes from ear to ear, this function, when for all A, B, this function is injective. Which means that we can use, the maps in AB can be seen as maps between f of A and f of B. An example of faithful functor, so faithful means that you can trust it, which means that you can check informations about A inside B. So it's a good representation of A. An example is the forgetful functor from groups to set. It is evident that homomorphisms between a group G and a group H are just a subset of functions between G and H. So the forgetful functor is faithful. And in this case, it really means that we can see objects in groups as decorated sets. The same is true for vector spaces, and the same is true in many other examples. And the motto here is that forgetful functors are always faithful. Which is funny because it means you can trust someone that forgets stuff, but it is true. Then what is a full functor? So the definition of full functor is the same, just I mean, it is about the same thing. I want that this map is surjective. Oh my God. Sorry, I have to leave for a second. Okay, I'm sorry, someone had activated the code. Okay, so so this is a full functor where this function is surjective. And let's make an example of a functor which is not full. So for example, the functor from group to set, the forgetful functor, is definitely not full because this function is not surjective. This is quite clear, I believe. But other functors are full. For example, the functor I provided you here, this one, as I mentioned to you, is full because every functor between categories which are of Posettal form can be seen as a monotone function between posets. So this is an example of a functor which is full. So here the motto is forgetful functors are not full, essentially never. Very good. So now I will tell you what is a natural transformation, and this will be the last topic of the first lecture. So what is a natural transformation? So given two functors, between two categories, a natural transformation alpha between F and G is a family of B morphisms such that, so again, what what is it? Let's see. So we have F of A, then we have G of A, then we have F of B, and then we have G of B, okay? And here we have A and B. And here there is a function, a morphism in A. So this happens in A. And instead, all of this, all the right part is in B. So let's call this H. Okay, so here we have F of H. And here we have G of H. So again, what is a natural transformation? Is a family of alpha A, alpha B. So is a family of morphisms alpha going from F of something into G of something of the same thing. So like in this case, we have alpha A and then alpha B, such that for all H, this diagram commutes. which means that this composition is the same of this composition. Okay. Let's try to make an example. So the example I would like to show you is about groups. So we have group, and here we can choose the identity, and we can choose the quotient by the commutator. Yes, very good. And now I will claim that there is a natural transformation pi that goes from the identity into the quotient. But this is more or less obvious from the previous consideration, because say that you have two groups, H and G, and a morphism F, then what you have is on the top you just get the identity and F. Oh, sorry, I should change the notation. No, it's correct. Okay. On the top, you just get the identity, which is F. Here, yes, here you get G over the quote. Here you get H over the commutator. Here you get, that's the mistake, this should be G. Here you get G over the commutator. Here you get F bar, and here you precisely have the quotient map, which quotient by the commutator, and which make this diagram commute by definition of F bar. So there are very natural example of natural transformation. That's why people call natural transformation, in fact. What's very important is that we can use natural transformation to define categories even. So maybe another example that you could try to show on yourself is that there is a natural transformation between this composition and the identity functor. And this natural transformation is pointwise an isomorphism, which means that each one of these maps, this one and this one, so the alpha i's are all isomorphisms. This one are all isomorphisms. In that case, we say that the natural transformation is a natural iso. So the last example of this lecture is very important, last example. And it's the example of G sets. So this is the one that I think no one has seen before in this group. And the idea is the following. So I told you that we can see a group G is a category with one object. We already discussed it, I believe. So we can define the category G set to the G. And what is this category? It's the category whose objects are functors from G to set when we look at G as a category, and then morphism are precisely natural transformation from F to G. Okay, so the objects are functors, and the morphism are natural transformation. So they look like this. And this might look to you as a very strange example. Maybe you will think But who knows this category? This is a category that I will never think about. Very good. I will define another category for a moment, and it's the category of G sets. So this category has objects, sets, together with a G action, okay? And morphism are G equivariant set functions. So this means that these are set functions such that if I take G times f of y, this is the same of f of G times y. When by times I mean the action in X, and this time is the action in Y, okay? So this is what means to be G equivariant. And now theorem, G sets is equivalent to set to the G. Now I should mention what equivalent means. So equivalent means that there is a function, a functor in this direction, and there is a functor in the other direction, such that this composition, so F, such that this composition is naturally isomorphic to the identity of this category, and the other composition is naturally isomorphic to the identity of the other category. So this is called equivalence of categories. And it is the correct notion of sameness between categories. It just means that the two categories are the same. They can be treated and regarded as the same category. Now, let's try to see these two functors in detail. So we want to define a functor which goes from G set into set to the G. So this means that we have a X together with an action of G. Yes? Now, which functor would you choose? I will give you 10 seconds to think about it. So the functor you must choose is the functor that takes this little element. Remember that in G there is only one object, and send it to X. And then it sends G to what? To SG, where SG is the permutation naturally associated to G. Because remember that an action can be also seen as a group homomorphism from G to permutation of X. So it sends little g to SG. Okay, so you send G to SG. And this gives you a functor which goes from G to set. Now we can check together that when you have X, Y, F, when you have a G equivariant function, then what you get is a natural transformation between F of X, sorry, I should change notation, between F of X and G of X. But after all, what is a natural transformation? After all, a natural transformation is just a function, because of how we chose the thing. It's just a function from X to Y such that when I look at the action of G on F, so Yes, I will write it down. This diagram must commute. But this is precisely the same of saying that F was equivariant. And so we get this functor which goes from here to here. And the construction in the opposite direction, so if you start from set to the G and you want to go to G set, what do? Well, you take your functor F and you send it to F of the point. And of course, this is a G set. I will leave you here in the sense that you can check on yourself. So this one was the last thing I wanted to tell you for today. You have your exercise sheet and you can do it and you can send it to me. And so we can discuss it. You can send me emails to ask questions, and next time everything will work without the problems that we had today. So thank you for joining. Tommaso, you can stop recording now, and